0. Okay, and there is a condition on the derivative. Okay. But we want to show something about the integral. Okay, this is what it. Again, we want to show that. So this is f cubed. It's not composition. You can understand. So yeah, this will not be x. This it will be t dt. Polynomial. F is not a polynomial. This is f cubed. This is f into f times f times f. Yeah. And we want to show that this is less than. So these are. Yeah, this is the first question. F dt cubed here, or no, it's not cubed. I think it is squared. Let me just check. But yes, yeah. So let's try this. If let's see how we can approach it. So remember, we want to show this, and here is very interesting thing, which is very important as a teller. For all x, you want to show this for all x, not that. So it's not of the type where you have to find show that there is an x for which it is true. It proves for all x. So let's try it. Let me just also have a check it. Integration by parts, right? Yeah, that might be a good idea, but in what way? Okay, so like this. Okay, so then what do you do? D of integral of f. No, so the what is it supposed to be? It's supposed to be like this. No. No. It will. So it will not. It will become. It will not work in. I think because it might work, but let's just do it then. So this would be f squared. Yeah. So if you want to apply integral by parts, so then it's like this, right? And then you have to, but the problem is you have to evaluate now this. So the way to do it, like you take the antiderivative and then you evaluate it at x and 0, right? So this is the first thing, I guess. And then in the second one, but it seems to become complicated, but I don't know, may work. I think you have to take. Is this correct? So that's what I've done, right? Ft is outside. I've taken its derivative. X dy. Yeah. So what is the formula? Right. Okay. Why? Yes. So the one that you integrate, you keep it as it is, which is what I've done, and the one that you keep outside, you take the derivative. So what's wrong that I've done? Yeah. Okay. Right. And no, even because I have forgotten by parts, so that's why I was able to ensure. But anyway, this is what it is. But then how does it help? Let's see that. How can we use this? Interesting. So this one will become something easy because of what is given to us. So I just substituted right away here. You can make this fx this, right? This is the cool thing, but then what? No, I have already put the limits. Yeah, I have put no, you have to put the limits, right? But f of 0 is 0. That's why that part is not occurring. Yeah. So whole thing is a function and you substitute x there. No, think about what I've done. It's not f of t. So this will be f of t. So there is a difference, right? You do the antiderivative first, and then you make the substitution. So when you do the antiderivative, then you don't put anything. Then it is just a variable, whatever. But then you put the value in the entire thing. Yes. Let's see. Hmm. Okay. Wait. So hmm. On this inequality, sorry. So on this inequality, you're multiplying. Yeah. Okay. Nice. Okay. Right. So just one second. Yeah. Just when you're this, we have made a leap here, but I'm sure roughly you people all understand. But try to also rigorously understand it. Just try to convince yourself that this is means you can't just say integrate both sides. You have to just say a few things, but just write it clearly when you're writing. Yeah, otherwise, you'll lose marks. If I have to say. Anyways, this is fine. Right. No, no. But just integrating this inequality, you have to just say that because it's true for all x, that's why you are able to, and so on. But anyways, yeah, that trick and all. So then you get this. Hmm. Okay. So yeah, at this point we should not make it x. So you're saying you should consider a different variable. Let's just call this y maybe. Okay. So the f prime y. Okay. But okay, you're getting some factors here. But let's see. So this is the second approach. So we already have two approaches. That's very interesting. This one is this. Yeah. Bring out that integral. Which one? This one? No. Look, this is a function of y. That is right. You should multiply by f of y. Okay, because then only the rightmost inequality will become integral, which will become a good, good to integrate. That's the change, right? Huh. Acha, let's now see, and also let's try to say it more rigorously. So we have this. Let's just simplify things first, and we have this, and this is true for all y. Interesting. Now, what should we do next? Integrate integrate this from 0 to x, right? Means that is the only thing. Left hand side thing, yeah, maybe it's not required. But see, it's not required, but it was now it's not required, right? Yeah, because now the problem is almost done. Now it's not required, and because that's not needed in the end result, but it was needed here while multiplying both sides by f prime, maybe. Yeah. Anyways, so this is the thing, and then you integrating it from 0 to x. So tell me, how will you integrate this thing? What is the meaning of this? Hmm. Right, so this is v of y. Okay, right. So then this is f v prime y. That's right. So then, right. Yeah, you will get the actual thing which is needed. Right. Then we are done. Right. That's a very nice proof. We get v square y. Sorry. Then you don't need all this. You have v square y, and you have to substitute x 0 to x, and you can substitute, and you'll get this exact thing. The two will cancel out. Nice. This is very nice. This is a very nice solution, right? So what did you do? You started from here, and then you built it up, right? Multiplying by f, and then integrating, and right, then multiplying by f. Yes, yes. Yeah. So the first thing he did is he started with this inequality, and so note that this will imply, and that's important. This will imply that f is positive because the derivative of because f is increasing, right? So f, it will imply that f is positive. So he's using that to multiply both sides by f, or rather all the three things, multiplying all this thing by f, multiplying this inequality by f. Okay, that's a good thing because this expression becomes nice, good to integrate. Anyways, so then this is true, this thing is true for all x, for all variables, for all values, for all inputs. So then you can integrate this, right? You can integrate both sides from 0 to y, right? And you get exactly this if you do that, because again f of 0 is 0, so this is just okay. So this is then good. So let me not erase anything now. Let me just go from here. Then here you multiplying by f, and it's good to just check multiplying by f again. And at this point, it is not really a surprise, right? Because this, if this quantity you see, then if you want to be able to integrate, then you want to multiply by its derivative, just like we did here. Just like so, you multiply by f on both sides. So that's what you do. Then you get this one, right? Star, and again you integrate. Yeah. No, so yeah, I'll say that. Just 1 second. Yeah, that's right. That's a good question, but that's just a logical thing. So you get this, right? And now it's done, right? Now it's you just it's clear. Now you just simplify, right? So this is easy, yeah. But now, okay, the equality. No, see, just think about this logically. What does it say? It says less than or equal to. So it is not asking for you to show equality, right? It is not asking that you should show that equality must hold, right? I mean, this implies this. what we have shown is actually more stronger. So less than or equal to, right? So if you show less than, then also is good. And it's not saying equality must hold. Yeah. No, equality will. Okay, yeah, that's maybe the right thing which you're saying. Yeah. So maybe that's actually correct, because this is less than, right? I mean, so this is where equality will come, though. Yeah, though if in any problem you are asked to show less than or equal to, if you just show less than, you are correct logically. But yeah, it kind of hints that you might be incorrect, because the question will not be so loose in that sense. But yeah, less than implies less than or equal to. But yeah, I think this is where what Raghav was saying is not this. It doesn't have to be equal to, because it's not given in the question. Or maybe I'm missing. Oh yes, it's given. Yeah, the question had equal to. That's why. Sorry. Yes, that's just my mistake. Yeah, but I think even then, right? If a function is less than the other, I think if you integrate, then the integral can still become equal. Yeah, integral can still become equal. Just think about it. I think yes, that's what we are doing. Antiderivatives. No. You can't take so the antiderivative is what is the antiderivative? No, that's what I was saying in the that's what I had said. So let me explain why taking derivative doesn't work. So this is the problem is this, that maybe we can take the, so you mean taking the derivative where? No, but which inequality? The given inequality or this one? Which one? The second one. Yes, but that is a problem, right? So if you call this a function gx, and if you call this a function hx, right? And if this holds for all x, let's say that this holds for all x. If you assume that for a second, then it does not imply that g dash x should be less than h dash x for all x. You are right. Yeah. So that's right. So then if you show this, then it's enough, right? So this will imply this. Yes. Yeah. Right. So if the derivative of a function is less than another function, then obviously the areas are also less, right? Yes. So I mean, maybe I should call this GT. That is right. So maybe that's what you had done in the solution, but I sort of misinterpreted, or maybe the way you wrote it, it seemed to me that you are taking the derivative of the integral. Yeah, something like that. But this is right. Obviously, you can. That's what Swagato has basically done. That he has shown that. Yeah, but see, but these are very nice solution. I couldn't say ingenious solutions. But there is what I'm trying to say. What my goal was in this problem, to show that this is just a nothing problem, in the sense that you can just do this without any. You can just do this by basic increasing decreasingness. What do I mean by that? What I'm trying to say is that, see, this is the thing. You want to show that this is greater than zero for all x, right? So this is the thing. So if you just consider this function, and once I say it very clear, because you want to show something for all x, so in all likeliness, or let me write this first. And when you want to show inequalities about related to these kind of things, it should be the first approach. You consider this function, and you know that f of 0 is 0, right? And you want to show that fx is less than, maybe I should have taken the other way, but doesn't matter. Let me just take the other way. Yep. You want to show that, okay, you want to show that fx is bigger than 0 for all x. So just show that f is increasing. Right? It's enough to show that f is increasing. So my point is that even much stronger thing is true. Right? That this inequality is not just true. Like if you consider this as hx and this as gx, it's not like hx is always less than gx, but in fact the difference is also increasing. It means it's kind of going farther apart, which is what would happen if this question was made from a natural source, right? This is just what should happen. Of course, that's not necessary, but yeah. So you want to basically show that fx is increasing. Sorry, no, you want to show that fx is positive. Sorry, you want to show that fx is positive, right? How do you show it? How do you show that fx is positive? So my point was that you just show that fx is increasing, right? So enough to show, this is very obvious, but enough to show f is increasing, right? Certainly it has to increase at 0, otherwise it will never become positive, but the claim is that it will always increase. Okay, and this should work in these kind of problems because you want to show something for all x, right? That's why it must usually increase, right? Yeah. So that is the thing. So how do you show that f is increasing? You take its derivative, right? Just take its derivative. So what will the derivative of f be? Let's try to do it. So let's do it without referring to Leibniz rule, though it is the exact same thing. But let's just see it, just using derivatives. You want to take the derivative of this. So how would this be? So this is the first thing. So you apply the chain rule. So this is 2 times, it's 2 times the function, right? And then you take the derivative of the function, right? You take the derivative of this. But then what is that? What is this thing, right? This thing is fx. So thus we can't use that fx. So we'll have to use, yeah, so that's bad notations. So I'll change this notation here. Sorry. Tx right? So this is fx minus f0, where the derivative of f is small f, right? Zero, and you want to take its derivative. So this will just become small f at x. That is important. Okay, so this will become small f of x, right? Is it clear that this is just the definition, right? This is the definition of this thing. It is the difference of the antiderivatives at those two. Well, that's not the definition, but it turns out that that's the case, and that's what makes calculating area so easy. That's really what calculus makes so effective. So anyway, this is thing, and similarly you can take the derivative of that side. So now we'll just do it. So we can yeah. So this will become f cube x. That's all. That's all, right? It will be nothing else. Okay, right? Or let's just check it, right? So this will be, if you take its, right? So if you take this, then what will this be? This will be, again, this will not be f cube x. It will be something else. The antiderivative will be something else. But whatever that will be, the derivative of g will be f cube, right? It will not be capital F cube. It will be something else. But whatever it is, right? It will be this. So yeah, very simple. So you want to show that this is positive. You want to show that this is positive. So at this point, it will be enough to show you can cancel the f, right? And show that this is positive. I mean, I'm just, yeah, change notations, but you want to show this is positive, right? So you want to show this is positive. You can have f outside. You call this h. You want to show h of x is positive. You do the same thing on h. You claim that h is increasing, you take its derivative, and you actually show that the derivative is positive. And it will actually work. Just do it. Okay. I'm not doing it because it's very routine and I have worked it out and it does work. So I'm not doing it. Okay. but just check it. So my point is that now this is just what we do all the time while proving that something is positive or an application of derivative portion, right? This is what you do all the time, and that's what the problem is. It's nothing fancy. Right? Yeah, so just having confidence that taking derivative integrals and just following the usual approach just works, but in 2 steps. And it's not a surprise that you take the second step because it kind of becomes more promising once you cancel the f. Yeah, it's kind of reducing. Take it again, it just works. This it will just reduce to this. So what Sogata has done is the reverse of this, which is why it's more ingenious. But yeah, this is also more straightforward. Okay, so any doubts with this? Is it okay? So this is just the same, and the theme kind of was that you could use the Leibniz rule, basically the derivative. So the Leibniz rule is useful in many other ways, but this was just one simple thing. Yeah. No, so it's better to never use the word Leibniz rule. It's better to just always use the fundamental theorem of calculus, right? That if you, yeah, that's the safest thing. So if you have this, then what do you need? So let's just see, like this. So by definition, this is fx minus f0 and f dash x, where there's not f dash x, but f dashed is equal to f. So when is this true? When is so the question is when you can apply the Leibniz rule reduces to saying when is this true? When is this true? This is not always true. Okay, the area is not always a difference of the antiderivatives. It's true when f is continuous. So if f is continuous, then you can do it. So you do not even need f to be differentiable. You do not need f to be differentiable. You just need f to be continuous. See, this integral exists in a lot more cases, even when f is not continuous. Okay, and of course I have not discussed it formally, but you understand it. And you must have seen like some box function kind integral you find and so on and so on. You can find the answers, and they are kind of correct. That's the thing. So, but this is not equal to this unless f is continuous. Okay, that's all. So if f is continuous, you can do all this simple. That's all. So you shouldn't no need to mention. Yeah. So the point is that when you take the derivative of this, you do not need f to be differentiable. That's what I was trying to say. That this automatically becomes, so yeah, that's, maybe I didn't say it. So if f is continuous, so if f is continuous, then f has antiderivative. This is not very hard to show, but I mean, I was going to discuss this when we're doing basically mean value theorem, Lagrange mean value theorem. It's just that basically, but you need some proper definitions and so on. But anyways, this is the first statement. Okay, so this is where pay attention. This is the first statement. The second statement is this that the f has antiderivative and the integral, which is completely different. Antiderivative is just something whose derivative is f. Okay, but this Riemann integral is equal to this is the fantastic part. Okay, yeah, so there are two things, right? And both are, and hence you can take the derivative without any problem. But you need both these things, right? The antiderivative existing and this being equal to the antiderivative, a difference of two differentiable functions. So it's differentiable automatically. F doesn't have to be differentiable. Small f doesn't have to be differentiable. Okay. Yeah. So this is the things, small things. Yeah. Okay. Yeah. Okay. So the last point is that if small f is continuous, then it has antiderivative, and because this integral is equal to difference of two differentiable functions, right? Because it's the difference of two differentiable functions, LHS automatically becomes differentiable. And that's just logical, follows logically, right? There's nothing, yeah. And so you can take the derivative. So that was just summarizing my point that small f just needs to be continuous. Yeah, right. But obviously in this question, we had to do the same thing twice. That's why we sort of needed small f to also be differentiable. But that's a different thing. So really these things are very clear if one just sees them conceptually and patiently works them out at one point, then it saves a lot of later on. Right. So I want to do the second question, which is also an interesting. So really, all problems in integrals which usually come, they just follow from a global thing. Like if you want to show something is less than equal to something, in fact, I want to show something is positive. It's usually that's just increasing because in these, especially integral problems, if they are of some entrance level, they will usually be like that. And this one is also somewhat has some sense that kind of thing. So if you want to calculate this, or you can also just add that, show that it exists, and then calculate whatever. So it's basically just an improper integral, just an improper integral question, right? Yeah. Yeah. Any ideas? Yeah, maybe next time I'll just send before the class also. But still, yeah, let's try it. Uh, this time I didn't send. So once again, that the idea is that it will follow from something more easier, or something, I should say, follow from something more general. Yeah. Hmm. Mm-hmm. So what are your bounds? So you have used it in this way, right? Right. So yes, that's right. I mean, yeah, integrating over t, right? Sorry, less than. Sorry, yeah. Pi by x plus pi, not x. Yeah, right, right. And sorry, yeah. So you will see that if you put zero as a lower bound, then it does not work, right? Certainly, you can check that, and it's not even true. So no. I mean, it is true, but it doesn't. It's not good enough. So it's a loose bound, and that putting zero as a lower bound is basically like take the limit inside, something like that, or just take the limit first and then do something like that, which doesn't make sense. So you have to put a sharper bound, and the sharper bound is, yeah. So the idea you have said is completely correct, but just that, yeah, the sharper bound is x minus x cube. Yes, but I do not want to say that use that, because that's a little controversial. I mean, if you, because no, but the point is that that doesn't tell you the. Hmm? No, this is much more specific than that. So it's a different thing. Look, if you take the expansion, what this thing is, yeah. First of all, what does it even mean? But you have to. But what I'm saying is that what we are using is that this is bigger than the first piece, and it's lesser than the first piece, and it's bigger than this piece. This is a little stronger than, right. This is, I mean, obviously, when it is done in a proper way, then all this is done together. But but point is that this is a well-known inequality. This is a thing that you can easily prove with just calculus, and you don't need the infinite series, and the infinite series will not even help you in that sense to prove. Maybe intuitively you can understand, but right, this you can easily prove. Yes, but we have to say it with yeah, that's right. But you have to say it with a bit more explanation. But yeah, anyways, you can say yeah. Right. But we have to prove this, and this is easy to prove. I'm not going to prove this. It's easy to show. Uh, Conceptually, it's a little difficult to show, but checking wise, you can easily just use derivatives and show it, and then just integrate it. So this is really nothing. This problem is not hard, but just that, this bounding thing, you have to be, yeah. So as I said, today I'm just not trying to do hard questions, but trying to do small easy questions. Okay, just because usually the last time we did some one big question, which was in fact not difficult. I ended up making it difficult. I think someone had sent me an easy solution later on, which was with manipulation based. But anyways, let me not distract ourselves. Yeah. All right. So let's go to the second theme of the day. Second theme of what today I had planned. The second theme is the following. Right? Um, we want something like infinite sets, okay, but zero area. So it is sort of like this, or maybe let me not even put the title. Can be wrong. See, so where am I taking this from? So if you remember, we had done a problem. Maybe all of you are not here, but let me just say it. We had done a problem where the question was, does there exist a continuous function from, well, to start with, this was a question. Does there exist a continuous function from R to R, such that uh, each output is attained even number of times. Yeah, I think all of us were here. Maybe Aniket was not here at that time. Yeah, but you can try this question. Okay, so f from R to R such that each output is attained even number of times. So any output here will be attained an even number of times. Now that could be 2, it could be 0, it could be anything, even, finite, obviously, even. This was the question. And we had shown that this is in fact possible, right? And we had discussed the motivation and all that, and we had come up with a function like I think like this, and then we said that we had to stop here, then have to go and stop here so that everything is at an even number of times, and so on and so on, right? But then we saw that, so the answer is yes, but then we had to do the same thing for f from 0 to 1. I mean, we had reduced the problem to this, but something like this, 0 to 1 to 0 to 1. Then what did we leave, right? Then we needed to sort of condense these things into condenses construction in 0 to 1, right? In 0 to 1. So for that, we needed to define a function which sort of does this infinitely many times, right? And we had to make some sort of construction. For this, we had to define a function, right? We had to do some construction here, which was like we had infinitely many things, but they were all adding up only till 1. And the answer to that was just a geometric progression, right? So a lot of things were adding up to only 1. So we want to just explore other objects, other elementary objects which have this kind of nature. Okay, and we look at this now. So I mean, yeah, just try to, for those who have not done it, just do this. Try to do this problem. Just try it. This is the general idea. Okay. Yeah. So what we want to say first is area of a set. Okay, I have to just say that a bit rigorously, and then I'll say. So let's say that you have a set on the subset of real line. Okay, so let's say that there is a subset like this spread out. I mean, these are important in probability type questions where you have infinite domain, okay, where the set of events could be infinite. So let's say that these are the points, these are the regions, the red part, and we want to calculate the area of the red part. So S is the red part. So first of all, we have to define area of S. What does it even mean? And it's a very simple concept. I mean, if you want to keep it simple, and we'll keep it simple, meaning that there are a lot of bad sets which don't have, and so on, so on. But simple is that area of S. Right. So any ideas as to how we should go about defining the area of a set? So this has to be a definition. Okay, how should we do it? I mean, this will help to clear up things moving towards integration also. But first, how should we do a definition? Then we can ask a question. Maybe the definition will be given to you in the exam and so on. But even then, it's good to have a hang of it. It's good to see how it comes naturally. Right. So the approach of the definition is, so approach, that is right. It will be something like that. Yes, that's what I was going to say. So we will approach via approximation. Okay. So yes, it is roughly that. But again, as I said, this is an oversimplification of the actual concept. But it will be good enough for the problem that we will do. Small problem, and then we'll also do a more interesting problem, and we'll see how much we can do. We'll approach this question via approximation. Okay. So what do I mean? So as Raghav is saying squares. So this is here, of course, we'll not use squares, but we will just use open intervals, which is the analog of squares. Or you can use closed intervals. You get the same thing. Okay. So what we will do is we'll say find a collection of, let's stick with closed intervals because that's more akin with the sense of squares. Find a collection of closed intervals. Okay. How should I say it? Because it's not a finite set, it may not even be a countable set. But let's say it's a count. Let's say that you can index it. So let's say that the closed sets are like this. In fact, you can always find, even if it's uncountable, you can always find a countables which will do the same work. I think that's true. But remember, it's not finite. It's infinite. So that's dot, dot, dot. So the step one, and maybe I should just say like this, to be very clear. Step one is to find a collection of closed intervals, but mind you can also find open intervals. It will be the same in the end. But find a collection of closed intervals such that the union, so point is it should cover the set. Union of these closed intervals covers the set. Okay, this is what of course we want. And right, so union of these closed intervals covers the set. And then the area is the area of S. Area of S will be defined as, so what should it be? As this is smaller and smaller squares, you find the smallest collection. You find that collection which gives the smallest. Yeah, so what does that mean, right? So yeah, so let us say like this. So if you find a collection, it's called the C1. Okay, so then I'll call A1 will be in my collection. So it will be the length. So basically what I'm trying to understand is what's the error? Okay. Or maybe not such the error. What's the sum? Okay. This is A1. This is the first approximation of the area. Right. Then you can take a different set, C2, and you get a different approximation. Right. A better one. So probably this A1 was like this. And then you found A2, which is better, even for some. Right. So find A2 and so on. Then my area, okay, the area of S will be I can't say the smallest, so I'll take the infimum. And I'm safe because I have 0 below. Okay, I'll take this infimum, which is the biggest among all the lower bounds of the set. Infimum over I of AI. Okay, so this is how I define the area. Okay, it is the infimum over all the areas that contain S. Okay, now this is not a correct definition in the sense that you need to think about it, right? If you get an infimum like this, okay, but then if you do the same process from the inside, that is if you under approximate and take the supremum, right? So you take closed intervals whose unions are contained in S, and then you take bigger and bigger such things. Then the supremums, right? The supremum of those things inside, maybe I'll call them small a, but I already have that, so maybe prime. if I take the supremums, okay, of the things that are contained inside, because AI prime is in some sense, yeah, it's inside S, and I take the supremum, right? Then this supremum will also exist if it's otherwise it's infinite. Anyways, that's fine if it's infinite. Okay, but the point is that this supremum and this infimum should be the same. If it is not the same, then it doesn't make sense to say what the area is. Okay, so and that's a little complicated, but the point is that then only the area is said to be defined, and that's very, very sensible, right? This is not enough what we have done, but let's just assume that this is the area. Okay, it's not, because we won't need the upper one. The upper Riemann sum is a special case of this. Okay, upper and lower, we just need lower. Okay, so anyways, the point is the question. What is the question? Again, I'm not asking the general question. I'm asking just a very concrete version of it, which we can, which is directly in the language of what we have done. I'm not changing the language right now. I'll give it in the test or maybe something like that. Anyways, so what is the question? What the question is, find the area of Q. Let's see. So what should be the area of Q? Of the set of all rational numbers. I realize that I can ask a better question first. What's the area of the naturals? Okay, so the claim is that it is zero. So why do you think it should be zero? No, you can't find a collection of closed. So your closed intervals should contain the set. So you can obviously find, if you cannot find, means you can obviously find to cover the set. You want to just cover n. Think about it like this. I mean, sorry. You want to find closed intervals which will cover it. Hmm. Okay. Okay, so let me start with the first thing that you said. That is um, length half on each side. So if you, yeah, right. So if, let's say, if you do that, then you get, I should have, yeah, but anyways, I plus half, I starts with zero. So if this is the first thing, then this will be like this just, and see these intervals can overlap and so on. There's no condition on all that. Okay, then what would you do, and what do you want to do next? So this is A1. Right. Um, right. Yeah, let me call that AK. Okay, this is also a valid cover. Yeah, this is also a valid, yeah, because it also contains N. Hmm. Hmm. But will the summation also approach zero? That is the important thing. No, no, no. So the summation is not 2 by k. Summation is infinite. Yeah, summation is 2 by k. So okay, let's say so. In this case, it will be summation is 2 by k, where I goes from 0 to infinity. That's infinity. No, but whatever the k is, it's infinite. You see, so yeah, the k is going to infinity, but the summation is still infinite. So then that doesn't prove the claim that the area is zero. Right? So is that correct? What I'm saying? Yeah. See, the interval lengths are going to zero. You're creating better and better covers, but none of these covers are good enough. Okay. Obviously, this doesn't say that this claim is wrong. It doesn't say that the claim is wrong, because the infimum could be taken over much other covers which are much better, maybe, or maybe there is no, I don't know. You have to think about it. This doesn't prove it. This doesn't prove that, and this doesn't prove anything in that sense. Hmm? No, but you should be sure that this is infinite. I mean, this is so for if for every k it's infinite, it's not decreasing or anything. So yeah, the total. So AI is a very interesting thing. It's a total thing. It's a total sum. Not okay, not AI, but that's the, yeah. That's so. This is CI. Yeah. Anyways, this is CI. The AI is, yeah, union over the collection. But we are quite certain that if this, I mean, it should be like this mostly. I mean, the thing is that the way we make these definitions is that we want this to be zero, right? I mean, these are the basis on which these definitions are made, right? Area of naturals has to be zero, and the definition is made like that so that it is zero. So the answer is correct, should be zero, but so the only issue is that we want to find good covers. Okay. Now go back to the point that I was making earlier, right? That you have a lot of things You have a lot of things. You have infinitely many things, infinitely many sizes, but they all add to one. Yeah, think about that question. Or in general, right? Just think freely, right? In the sense that, so here we had this size, then we had this size, and we had this size. I mean, in the sense that these can be taken as the covers, smaller and smaller covers, but then they add up to one. That's what we did, right? And you can always do this by taking, I mean, so my point is that the very obvious kind of cover to do is just to take the geometry progression. That will at least bring you to finiteness. Right? So this kind of constant cover will not work. A cover which has constant size will never work because it will add up to infinity. Right? You want your things to go to zero. So here you can take a cover of size half. So I'm not mentioning the exact things, but then you take, I mean, you can write it. You can have to vary this 2 to the power I or something like that, 2 to the power j, something like that. But the point is that, yeah, you take these covers, right? 1 by 8. This still doesn't do the problem though. Okay. 1 by 16, 1 by 32, and so on. Right? You see? Now, then you can, then what have you done? You have found a cover, right? You have found a cover. So let me write that clearly, right? We have found a cover such that we have found a cover C such that area of the cover is equal to 1. Okay, and obviously a C contains n, right? So what have we shown? That there is a member in this thing. So this is, that's where I made the mistake maybe, but in fact it's not. I mean, just to, I was saying to simplify it, because this, I'm saying that there are not countably many AIs, but there are just many covers. Okay, but my point is that we have found a cover which is 1. So this means that the infimum should be less than equal to 1. So we can say that the area of n is less than equal to 1. Right? We can safely say this. Now the task for you guys is to actually show that it is 0. Okay. So that's the next thing that you have to try for. Just try it. Okay. This is the starting of a very interesting concept. Okay, and I will not go into theory, but I'll discuss more questions. Okay, because this is important to have these varieties and so on. And yeah, so I'll discuss this next day. Okay, so maybe I will do the same thing tomorrow also, 8 p.m. to 9 p.m. I think because exams are also coming for those who are writing exams, especially this year. But in general, obviously, these are yeah. So I mean, these are interesting. Yeah. Just, yeah. Think about it. Yeah. Let's everyone will try it and then we'll do it tomorrow. Yeah, it will be something like that. But let's see. Yeah. Okay, because think about it clearly, because then I will try to make it harder. Okay, then we will connect this with integration and some questions there. And so this is what I'll do tomorrow. Continue this, and then I'll go into a different theme, a third kind of theme, which will take it. Okay, so then same time we'll meet tomorrow also. Yeah. Okay. So this week I'm probably not going to take any theory class on calculus. Next week maybe we'll do. This week we'll just do these themes. I think it's a little faster because exam is coming, and then we can go deeper into the topic.